Hello, welcome to my video series of data structures. This is part 4 of module 5, the tree data structure. In this video, we will introduce the Splay tree. In the previous video, we introduced the AVL tree. Unlike a basic binary search tree, an AVL tree guarantees O log n time complexity for search, insertion, and deletion operations, even in the worst-case scenario. This efficiency is maintained through 4 rebalancing operations, which ensure that the tree's height remains in O log n throughout the entire life cycle of the tree. One limitation of the AVL tree is that it cannot leverage data locality to speed up data access. The concept of data locality suggests that when a piece of data is accessed, it is likely that the same data and its neighbors will be accessed again in the near future. For example, accessing a variable in consecutive lines of code, or iterating through adjacent data elements in a for loop. In an AVL tree, if the data being accessed is located in its lower levels, repeated accesses of the data and its neighbors may become very slow, despite that the time complexity still being O log n. To address this limitation, we introduce the Splay tree. In a Splay tree, whenever an element is accessed, whether through search, insertion, or deletion, it is lifted to the root of the tree. Its subtrees are also reorganized to be closer to the root. This restructuring improves the efficiency of future accesses to the same element and its neighbors. While the Splay tree also maintains the O log n time complexity over a series of access operations, a single access operation may have a small chance to run in O(n) time. Now, let's delve into the details of the Splay tree. Similar to the AVL tree, which defines 4 rebalancing operations, the Splay tree employs 6 splaying operations. Among these, 3 operations are symmetric to the other 3. The purpose of these splaying operations is to move the element being accessed, whether it is being searched, inserted, or deleted, to the root of the tree. Additionally, these splaying operations also aim to balance the tree, reducing the time for future accesses. Below, we will explore the 3 primary splaying operations one by one, excluding their symmetric counterparts. First, consider the scenario illustrated in the left figure, where the node beta is accessed, and it has no grandparent. This case is called the zig case. To handle the zig case, the splaying operation involves performing a rotation between beta and its parent alpha. This operation is identical to the single rotation operation used in the AVL tree. After the splaying operation, observe that the accessed element, beta, is lifted to the root of the tree. To analyze how the splaying operation affects the levels of the subtrees, we label their levels using the green numbers. These levels represent the distance from the root to the subtree. For example, before the splaying operation, the subtree X has a level of 2, indicating that the path between the root node alpha to X has a length of 2. By comparing the depth of the subtrees before and after splaying, we can summarize the following changes. The left subtree of beta, X, is lifted by 1 level. The right subtree of beta, Y, remains the same level. Conversely, the subtree Z is lowered by 1 level. The second case is illustrated in the left tree, where the node gamma is accessed. In this scenario, gamma is the right child of beta, and beta is the left child of alpha. This case is called the zigzag case. To handle the zigzag case, a double rotation is performed between gamma and beta, followed by between gamma and alpha. This splitting operation is identical to the double rotation used for rebalancing in an AVL tree. After the splitting operation, the accessed node gamma is lifted to the root. Then we compare the levels of the subtrees before and after splitting. The two subtrees of gamma, B and C, are both lifted up by one level. Subtree A remains at the same level, while subtree D is lowered by one level. Overall, one subtree is lifted by one level, and the average depth of the entire tree tends to decrease. This reduction in depth promotes a more balanced tree structure overall. The third case is the zigzag case, as illustrated by the tree on the left. In this scenario, the access node gamma is the left child of beta, and beta is the left child of alpha. To handle the zigzag case, we tilt the tree down by making gamma the parent of beta and beta the parent of alpha. Note that this operation is unique to the Splay tree and has no direct equivalent in the AVL tree. After splaying, the accessed node gamma becomes the new root of the tree. The left subtree of gamma, A, is lifted by two levels. The right subtree of gamma, B, is lifted by one level. Overall, the average depth of the subtrees remains unchanged. With this, we have now discussed the three primary splitting operations. It is important to know that there are three additional splitting operations, which are the symmetric counterparts of the ones we have just covered. In addition to how they restructure the tree topology, the splitting operation differ from the rebalancing operation of the AVL tree in how they integrate with the data access operations. First, the splitting operations are applied during all three data access operations, including search, insertion, and deletion. In contrast, the rebalancing operations of the AVL tree are only performed during insertion and deletion. Second, the splitting operations are always executed regardless of the tree's balance. On the other hand, the rebalancing operations of the AVL tree are only triggered when an imbalance is detected. The implementation of the Splay tree can be achieved with making minor modifications to the AVL tree. First, we integrate the splitting operations into the search operation. As shown in line 12 of the provided code, the splitting operation ensures that the accessed node is moved to the root as part of the search process. For the insertion operation, we just replace the balance function with the Splay function. This is shown in line 11 of the provided code. Similarly, for the deletion operation, we replace the balance function with the Splay function. This is shown in line 14 of the provided code. It is important to know that the places where the Splay functions are invoked are identical to those for the balance functions for the AVL tree. As a result, the splitting operations are performed bottom-up recursively, following the path from the accessed node back to the root. Now, let's walk through a real example to illustrate how splitting operations are performed. Assume that we have a highly imbalanced tree storing the numbers 1 through 7, and we are accessing the number 1. First, we identify this as a zigzag case and perform the corresponding splitting operation. This operation tilts the subtree rooted at node 1, which makes node 1 the parent of node 2 and the grandparent of node 3. Next, we identify another zigzag case and perform the corresponding splaying operation. This operation lifts node 1 even closer to the root. Finally, we encounter one last zigzag case. After performing the splaying operation, node 1 is lifted to the root, completing the data access operation. It is important to know that in the previous example, we only performed the zigzag splaying operations. Initially, these operations may not seem to reduce the average depth of the subtrees. However, after a few splaying operations, it becomes evident that the overall tree structure becomes shallower, improving access efficiency. To understand why the tree becomes shallower, let's revisit the zigzag splaying operation. After a single splaying operation, the right subtree of gamma often becomes a relatively large tree. This is illustrated by the subtree highlighted with purple shading. In this case, the right subtree of gamma, B, is likely to be larger than the subtrees C and D. Since the splitting operation lifts the larger subtree B but lowers the smaller subtrees C and D, it likely reduces the overall depth of the nodes in the tree. Next, we analyze the time complexity of the data access operations in the Splay tree, including search, insertion, and deletion. Similar to the AVL tree, the splitting operation are integrated with these data access operations. Therefore, we refer to them collectively as access and splay operations. For AVL trees, we have proven that the access and rebalance operations run in O log n time. This is because the rebalancing operations maintain the tree's height at O log n. However, this guarantee does not hold for splay trees, since splitting operations do not account for the subtree heights, and therefore cannot ensure the O log n time complexity. In fact, as shown in the earlier example with a highly imbalanced tree, a single access and split operation can take up to O(n) time in the worst-case scenario. Fortunately, a tighter bound can be established for the access and split operations in a split tree. In short, while the first few access and split operations may take linear time O(n), the topology of the tree is continually adjusted by the splitting operations. As a result, subsequent access and split operations gradually achieve O log n time complexity. Moreover, when considering a series of access and split operations, their average time complexity remains O log n, even in the worst-case scenario. While the detailed proof is complex, we can outline the high-level idea behind the time complexity analysis. First, recall the three splitting operations: zig, zigzag, and zigzag. On average, none of the operations increases the depth of the tree. In fact, one of them, the zigzag case, can reduce the depth of the tree. Assuming each of the three splitting operations has an equal likelihood of being executed, the height of the tree tends to be decreased after a series of splitting operations. As the height of the tree approaches its minimum, it converges to O log n, resulting in a linearly balanced tree. The next question is, how many splitting operations are required to minimize the tree's height? For the height to be minimized, the average node height reduction achieved by each splitting operation, multiplied by the number of splitting operations, must exceed the sum of the initial heights of all nodes. This ensures that, over time, the cumulative effect of splaying operations sufficiently decreases the overall height of the tree. First, let's determine the average node height reduction achieved by each splaying operation. Recall that only the zigzag splaying operation is capable of reducing the average node height. This operation lifts an entire subtree by one level, reducing the heights of all nodes within that subtree by 1. Now, the question becomes determining the average size of a subtree. Recall that the discussion is made under the assumption that the height of the tree is O(n). Otherwise, if the height of the tree is O log n, it is trivial to prove that all data access operations will also run in O log n. When the height of the tree is in O(n), the average subtree size is also O(n). For example, in the highly imbalanced tree shown on the right, the subtree rooted at T1 has a size of n, the subtree rooted at T2 has a size of n-1, and so on. By summing these sizes and dividing by the total number of subtrees, we obtain that the average size of these subtrees is approximately n/2. In this scenario, the average subtree size is in O(n). Next, we calculate the sum of the heights of all nodes. Again, assuming the height of the tree is in O(n), we observe that the height of T1 is n, the height of T2 is n-1, and so on. Adding these heights yields a total sum of approximately n²/2. Thus, the sum of the heights of all nodes is in O(n²). Now, we know that each splaying operation can reduce the total height of the tree by O(n), while the sum of the heights of all nodes in the tree is O(n²). In this case, we need to perform O(n log n splaying operations, resulting in O(n² log n total height reductions. This guarantees an effective upper bound on the total heights of all nodes, which is O(n²). It is important to know that only performing O(n) splaying operations is not sufficient, as it would result in a total height reduction of only O(n²). This reduction matches the same order as the total heights of the tree, and therefore it cannot serve as a valid upper bound. After determining the number of splaying operations required to balance the tree, we proceed to analyze the time complexity of a single access and splay operation. Recall that no splaying operation increases the depth of the tree. This means that after balancing the tree using O(n log n splaying operations, future accesses will consistently run in O log n time. As a result, only O(n log n splaying operations are required throughout the entire life cycle of the tree, regardless of the total number of data accesses. Now, we visualize the O(n log n splaying operations required to balance the tree as the cyan box, representing the cumulative effort needed to balance the tree during its life cycle. Since the splaying operations are performed alongside with data access operations, we group them with n data access operations, represented by the yellow box. To determine the number of splaying operations expected in each access and splay operation, we divide the total number of splaying operations, O(n log n, by the total number of access and splay operations, n. This gives an average of O log n splaying operations per access and splay operation. Since each splaying operation requires only constant time O1, the time complexity for the splaying part of an access and splay operation is O log n. In other words, the cyan part of the strip representing the splaying part of an access and splaying operation, takes O log n time. Then let's consider the access part of the strip, represented by the yellow section. The access part involves traversing tree from the root to the target node. The access part of an access and splay operation also takes O log n time. This is because both the access and splay operations are applied to the same set of nodes in their traversal path of the tree. Therefore, the number of access and splay operations must relate linearly in a single access and splay operation. As a result, each access and splay operation, whether it involves search, insertion, or deletion, runs in O log n time. However, it is important to know that this time complexity is amortized and applies only when performing a series of On or more access and splay operations. In such case, the overhead of splaying is evenly distributed across the access and splay operations, ensuring an amortized time complexity of O log n per operation. For an individual access and splay operation, its worst-case time complexity remains On if the tree is highly imbalanced. Finally, let's summarize the splay tree by comparing it with the AVL tree. The splay tree defines 6 splaying operations, which are always performed alongside with the data access operation, such as search, insertion, and deletion. In contrast, the AVL tree defines 4 rebalancing operations, which are only performed during insertion and deletion, and only when an imbalance is detected. For a single data access operation, the splay tree has a worst-case time complexity of On, while the AVL tree guarantees a worst time complexity of O log n. However, for a series of On access operations, the splay tree achieves an amortized time complexity of O log n for each operation. Finally, the splay tree is particularly effective for local data access, as it moves recently accessed elements closer to the root, optimizing future accesses to those elements. Thank you for watching, and see you next time.